Hi, everyone. So we're going to finish up Griffiths Chapter 9 if you're using the first edition, and then 8.5 if you're using the second edition. Sorry, I didn't notice that the different editions have different sections in Griffiths. I'm also going to, so Griffiths also has, I think, a section on asymptotic freedom, which is this idea of the running of the coupling constant. Where he dives into a little bit, but I think I'm just going to cover those conceptually, so I'm just going to wrap those up at the end of this lecture also. So make sure to stay tuned for that. Don't just click off as soon as the section is over. Okay, so this section is going to be considering the pair annihilation in QCD, where you have a quark and anti-quark run into each other, they annihilate, and therefore creates gluons or other quarks, depending on what the decay products are. Okay, so we're going to deal with this particular Feynman diagram. Remember that the Feynman diagram for Griffiths is have time going up, right, instead of across. So I'm going to translate this to the Thomson version, which is where we're going to have time going to left to right. So we have a quark coming in, right, with some momentum P1, okay, and then some spin 1, and then some color 1. So now we're tracking a lot of different things, right? This quark actually runs through, it becomes the propagator, and then you have an anti, and the quark coming out, but then this is actually an anti-quark coming in, right? Color 2. And then at these vertex, right, we're going to emit gluons. And then basically this will be basically a quark to QQ bar to glue diagram. Specifically, this is going to be the T channel because this one that's going down. Right? I'll even label these P3, S3, C3, and then P4, S4, color 4. Okay. We practice a lot of Feynman rules already, so I'll just give you the matrix elements for this. Okay. So the matrix elements for this is going to be you have these, this anti-quark part. Let me just write that in blue, right? So in red, okay. And then you have this vertex factor, right, from this. And then from there, right, you go actually to the gluon, because that's where the vertex is connected to, right? You have this little polarization and the color of the, the octet state of the gluon as this A8 component vector. Okay, then you have we're going to do that in green, right? Then you have the propagator here. And then you run through the other vertex where we start off at the gluon, right? You start off at the gluon, and then you end up at the quark. I think the book decided to just factor out this lambda, alpha, gamma, mu. Okay, just to see that the vertex factor is here. Okay, all right, so and in this case, I think he also left off the star of the gluon polarization until the end, but I think I still see that there, so I'm not sure what he's mentioning that. Okay, so if we were to do a little bit of kinematics with this, right, where q squared is basically q squared minus m is going to be whatever q, right, it's going to be equal to P1 minus P3, right? And if you square that, then you end up with this cross between P1, P3, and then there's a negative cross term, right, which is the 2 times P1 dot P3, okay? And then if you subtract this to the mass square, what you'll get is that you're just going to get the minus P1 dot P3 because over here, right? P3 right, is a gluon. So this is actually massless. For gluon, go to 0. Right, this is mass of the quark, which is whatever that is, and this is actually the mass of the quark. You subtract these two, right? Then you get 0, and then you just end up with that. Okay, so that what's going to allow us to replace this little piece down here. Okay, and then if you simplify that a little bit, and then unfortunately, Griffiths does use this slash notation, but we're gonna not deal too much about this polarization stuff, this slash notation, because what we're gonna do is we're just gonna kind of look at this more conceptually as opposed to trying to do all the trace stuff anyway. Because as I told you before, right, any calculations we do here is actually just the first order, and you are only calculating one of infinite number of diagrams that you need to in order to make it good predictions anyway. Okay. So, this the Lorentz invariant matrix element kind of factorizes, let's say, right, to basically what you have is you have the spinner part here. This has to do with the spins, right, and then you have the color stuff here that deals with the color part. Okay, all right. So that's one of the diagram. Since the gluon that's coming out, right, on the right-hand side here are identical particles, we will have a U channel where we swap the where we have the crossed outgoing particle instead. So a gluon will go out the other way, and then let's see what this diagram looks like. Okay. So for the U channel, okay, so this is once again, right, with the time going up. I'll translate this to the Thomson convention, right? I'm not going to write all the P's and the C's and the S's, but hopefully you see what this looks like, right? You have you have an incoming quark, you have an incoming anti-quark, right? As opposed to these gluons splitting out into their respective direction, they actually cross each other, okay? So this gluon P3 actually comes from this vertex. This gluon P4 actually comes from this vertex. So these are different diagrams, so you have to account for them. And then if you do all the Feynman rules, and then the little bit of simplification, right, and separate factorize the color part versus the spinner part, you end up with this matrix element M2 down here, okay? All right, notice that is very similar to what we have up here, but things are in slightly different order, okay? So you have the E's and the P's in different orders. All right. Okay, I think this is basically the same still, yeah. Okay, and lastly, we also have the S channel, okay? So remember, this is time going up, right? In this case, right, the quarks literally just slam into each other, and then you have a gluon coming out, and then this gluon decay into two different gluons, okay? Right, this is the S channel. This one is the U channel, okay? Okay. In this case, we do all the Feynman diagram stuff once again. What you end up with, right, is this, right, where this part deals with the spinner part, and then you also have the color factor here, okay? This one is a little bit different, right, because right now you're dealing with this gluon, the 3 gluon vertex, okay? Okay, so why are we doing this, okay? Because you can't really compute anything with this anyway. What we're going to do is actually we're going to pick a particular case, which is actually the decay of the eta C meson. The eta C meson, it's going to be a little bit of homework problem for you to look this up in TDG, but hopefully you can find it easily. It's a CC bar meson. It's also known as a charmonium, kind of like play on words of like lithium or something like that, right? And then you just put charm, since they're made of charm quarks, right? You call them charmonium. Okay, and it's all these properties. So let's see, I think I did decide to save some room for this. So this decay, right, this is not a stable state, and therefore what you have is, if I can write still, that'd be great. Right, you have a charm, and then you have your anti-charm, right? They come in, right? They annihilate, and then it decays into this stuff. Or you can also have the T channel, right, where you have this, right? Right, and then you also have the U channel, which is the cross version. Okay, so these are the CC bars coming in, right, and they decay into gluon. The idea is that we're going to have CC bar going into glue. Okay. This is not the only possible way for it to decay. In fact, a lot of these gluon, since gluons are not going to be these stable particles, they actually go into like, maybe like a lambda particle, or 2 lambda particles, or some hadrons. Okay, and so usually these are labeled 2 hadrons. Actually, in fact, what they do is like you have CC bar going to just a bunch of combinations of hadrons. Okay, but the calculations we're going to do is with the glue, okay, or at least the ratio we're going to get. Another way for the charmonium to decay is also with the same type of channels here. Actually, you have the C and the T and the U channel only, where you have the charm, instead of spitting out a gluon, it can spit out photons, right? Because the charm has an electric charge of 2/3, right? Q of charm equals to 2/3. Okay, so therefore it actually does couple to the electromagnetic force. Of course, you're going to have the same thing with the U channel, right, where the photon spits out this way, the photon spits out this way. You cannot tell the difference between the two because the 2 photons look the same to you. Okay, you don't have the S channel, of course, because, right, the photons is not coupled to itself because it has no charge. Okay, in the charmonium, right, just think about this as kind of a little blob, and you have 2 charms just kind of sitting near each other, right? So what we can do is go to the rest frame of the charmonium. Okay, we can think about both of these are at rest relative to each other, right? And therefore, right, P1 and P2 is just MC. Well, we don't have to deal with the C. We can just set that to 1. And what happens is that this thing will decay into 2 different gluons. You have 2 gluons coming out, right? So these are the gluons coming out. And what we're going to do is we're going to set this along the Z direction just to make things simple because they're just rotationally symmetric anyway. Okay. And what happened is that P3, which is the, let's say this is P3, this is P4, right? We'll have, whatever the mass of that particle is, right? In this case, the gluon, and times the momentum. And P4 will be the mass of the gluon times the momentum. Okay. In this case, right, and then we can compute a bunch of dot products. So now that we have all these 4 momentas, right, P2.P3 and P1.P3, P1.P4, that's going to be MC squared, right? That's basically the mass of because, right, initially P1 is initially at the rest frame, then anything dot that will just pick up the energy term. Okay. P3.P4, right? So, right, those are the 2 guys here, right? It's actually technically going to be equal to 0 because, right, both of those should have a mass of 0. Okay. All right, but we don't really need to worry about that because what we're going to worry about is actually when we're dealing with the, go up here, right? What you end up having to calculate is actually P3 dot these polarization vectors and P4 dot polarization vectors. Okay, in this case, right, these will also be 0. Okay. Okay. Similarly, any of these 4 vector dots epsilon 3 will also be equal to 0. Okay. All right. I'm not going to go through all the math. I don't think I'm going to even have you guys do it. It just turns out to be a lot of algebra steps. Okay. But what we want to do, since the this decay, right, are similar between the two. Okay, there's an additional diagram for the gluon, but which you don't have with the photon. But the calculations are actually the same between the electrodynamic version and the strong version, right? The only difference is that the strong version is going to have this additional color factor, which is this stuff here. Let me try to highlight this. Oops. Right. These A's has to do with the color of the gluons. These C's has to do with the color of the quarks. These Gauss matrices, right? Those are the things you connect the different colors together, right? You have this over here. This is just a summation sign. And then you also have this. You have the colors part down here. And what I want to make sure to denote is that, so whenever he has a curly brace, alpha, beta, that signifies the anti-commutation relation, meaning you're actually calculating alpha, lambda alpha, lambda beta, plus lambda beta, lambda alpha, where you have the square brackets. Those are the regular commutation relations, where you're calculating, right, lambda beta minus lambda beta lambda alpha. Okay. Whew. Okay. Ugh. So the A to 0 is also a spin 0, meaning this angular momentum is equal to 0. It also has negative parity. That means when you swap the spins, you actually pick up an additional negative sign. So the way you want to calculate this matrix element summing over all the possible spin is that you can either have the charm being spin up and the anti-charm being spin down, or vice versa, the other way. Okay, and when you do that switch, there's going to be a negative sign between the two. Okay, because of this negative parity, which we're going to talk a lot more about coming up in chapter 11 when we have to deal with the weak force. Okay. All right. Just like QED, right? When we did these in annihilation process with E plus E minuses, right? Some of the current contribute, some of them are 0. So Griffiths also did all of this, where you found that, well, these currents are 0. The non-zero current, so this is a summation sign. He writes up the summation signs. Okay. This is actually the only part that's not 0. Okay. This V2. So remember, this means P2, and this means P1. Okay. Those are the only non-zero parts. Okay. So therefore, right, when you put all this together, the matrix element summing over all spins, you end up with just this negative I square root 2. There's a 4 down here for some reason, right? It's just kind of got carried down. Okay, and then partially canceled out with this other 2. You have the GS square, right? That's the coupling for the strong force. You have this cross product between the two polarization of the outgoing gluons. You have these color factors, right? So this all have to do with the color part of it. Okay, so in this case, okay, the color factor is actually going to be 1/8 times this whole thing. Okay, these two A component vectors stack on top of each other, and it's going to get rotated, right, with these lambda matrices. Oops, nope. Before that, right, these color right? It's gonna the quark color components will be multiplied with the Gell-Mann matrices, okay? Because those are the 3x3 with the three component stuff. And then what we're going to do is we're going to have to sum over these alpha and betas for these different gluons. Whew. Okay, so in general, right, so the gluons can take on 9 different color combinations, okay? Since we're dealing with this eta C, right, these two quarks has to have opposite color from each other, okay? So therefore, the only ones that have where you connect these gluon to also have, opposite color for each other, right, is these green, green, blue, blue, right? Well, green, green, blue, blue bar, right? So you have the chance where the quark number 1, the quark is actually red, and then the anti-quark is anti-red, with the square root of 2 as the amplitude for that. And then you can also have the same chance of being blue. All right, and then the other ones where you have also the same on both is actually number 8, right? Okay, where it can be red, blue, and negative twice the amplitude of being green, green bar. Okay, you also have this color singlet, okay, which is 9. Okay, and what Griffiths decided to do is just only do the one that's for the 9. Okay. And what we're going to do is we're actually going to have to probably multiply by 3 afterward to account for that. Okay. All right. If you compute the color factors, right, you put in this anti-commutation relations between lambda alpha and lambda beta, right? We're going to do a little bit of this in our homework. Okay. What ends up happening is that you end up with basically this factor in front with your color factor. And we still have not dealt with these octet gluon vectors. Okay. So these octet gluon vectors, if you just line them up and multiply them to each other, and then add up all the different pieces, okay, for all the possible ways, okay, you end up with a factor of 8. Okay. And therefore, when you do this calculation, this A alpha for the 2 outgoing gluons actually gives you a factor of 2 times the square root of 2. So if you combine that, plug that over here, what you end up with is that the color factor just turns out to be square root of 2 over 3. Ugh. Okay, so now that we have this color factor here, so this whole thing turns out to be square root of, this whole thing times 1/8 turns out to be square root of 2 over 3. Okay. Now, right, if we plug that back into here, let me grab this, okay. Oops, should just use the keyboard. Plug that back into this, okay. So the color factor is 1/8 of that. Okay, so this times 1/8, that means I have to put an 8 up front, which mostly cancels out with this one. Okay, so this whole factor here, right, turns out to be square root of 2/3, and then E3 cross E, epsilon 3 cross epsilon 4. We did that, right? That should just, it just gives us a factor of 1, right? Let's see if we get this right. Okay. And then we multiply both sides. I think we do need to pick up a factor of I here. Okay. And then this actually multiplies together, negative I, to give you this -1 in front. And then basically what you have here is square root of 2 times 2 times square root of 2 over 3, right? So this will be, let's see, so this will be 8 over 3, right? And then for whatever reason, right, so this will be 4. Did I miss a square root of 2? Yeah, I think I missed a square root of 2 here. And then you have the square root of 3. Oh, of course, yeah, I screwed that up because the square root goes over everything. And then you basically have the matrix element as this -4 square root of 2/3 whole thing. And then you still have this g square here. Okay. So Griffiths does is cross conversion from matrix element to cross section a little bit different. What he does is especially in this case, is he goes to the non-relativistic regime, which is true in this case actually because you have the two charm quarks just kind of sitting next to each other. Okay, so if we plug this cross section, this matrix element into the annihilation cross section in chapter 7 of Griffiths, what you end up with is that the cross section turns out to be just the square, right? Turns out to be 2/3 times this whole factor here, okay? And there's a reason why I didn't say that whole factor there, because that whole factor there is the same thing as E plus E minus, right? Remember you have this plus E minus radiating photons, or you can have E plus E minus radiating photons, but then they have this cross thing, okay? So this is the cross section for that process, okay? The reason we're trying to compare these is because notice that these are the same as each other, except the difference is 2/3 and the coupling constant, okay? In fact, okay, the calculations for this, right, doesn't actually give us the actual cross-section for the strong version because we only calculated 3 out of infinite number of diagrams, okay? The reason we're comparing this to the electromagnetic version is because, right, so let me just do an example quick. So in our strong version, right, we'll have a charm, we'll have an anti-charm. Let's just deal with the T channel. Okay, spits out gluon, spits out gluon. Okay, so that's one diagram. So there's a completely analogous version of this, right, in QED. Charm, spits out photons. Okay, right. There's another version of this where, well, let's do another order. Right, you have the same diagram. Oops, this arrow's backward. Yeah, I'm even gonna leave out the labels, okay? Since the gluons are charged, they can, I'm gonna try to find one that's actually the same thing where you can have this quark here, right? Link an extra gluon to here, okay? Actually, I think I probably want to just link this way, right? Since these are colored, right? So this is all QCD, and this is all QED, right? So in QED, you can do the same thing, okay, where the photon can be initially exchanged between the quarks. This is known as the initial state radiation, okay? And this can go on forever and ever, where you can just go to higher and higher order diagram. Okay, the neat thing about this is that since the QCD and QED versions of these diagrams, they're all kind of parallel to each other, right? There are some diagrams that's not allowed in QED. You know, so of course you can't just connect photons together over here where you can do this. So there's going to be a little bit of a factor between them. And what we're going to see is that in the homework, we're going to see that we cannot compute the cross section for charm decaying to gluon. What you can predict is actually the ratio between the electromagnetic process and the strong process, okay? So that's kind of a fun thing to do, okay? All right, as I mentioned in the beginning, I'm going to also talk about the running of the coupling constants. So Griffiths covers this in I think 9.4 in the first edition, right, and then 8.6 in the second edition. He does a lot more math than I would do in this because, but the thing is, I still want to give you guys kind of a conceptual overview of what that is, because you may see this, especially those of you working on the Large Hadron Collider in the future, okay, where we deal with the strong force all the time. Okay, so one of the things is that it's really funny is that the coupling constant are actually not constant. Okay. Okay. If we look at this plot here, this is plotting the coupling constants for electromagnetic forces, right, as a function of Q, right, meaning, so maybe you have E minus, E plus here, right, right. Each of these comes with, basically alpha EM, right, alpha E of coupling, right. So how does this, and this coupling is actually proportional to the momentum exchange between the electron and positron. Okay, right, and hopefully you can see that this is actually going up as a function of Q. Okay, so that's a little bit interesting, right? In fact, this number that we've been using, 1 over 137, is actually a low energy limit. Okay. Okay. So it approaches this number at very low energy. So why does this happen? Okay. So one of the things we talked about last chapter when we were probing inside a proton, right? As Q increases, right? What happened is that you're probing things at a shorter and shorter wavelength. Okay. So I can draw this, right? Where you have an electron coming in, and then you have a proton, which is a composite particle, right? At very long wavelength, right? You're probing the entire proton, right? But as you increase this Q between them, the energy of this Q, right? That you go to shorter and shorter wavelength, you're actually probing inside the proton to the individual quarks instead, right? Okay. So when we're far away from an electron, let's say we're scattering 2 electrons off each other, right? Okay. When you're far away, okay, they don't actually exchange a photon directly. Well, there's an exchange of photons between them, right? So you have the scattering, okay, okay. But the electron, right, has its own electromagnetic field, right, and therefore actually can create kind of like virtual photons all around itself. I'm trying to draw this as kind of a shielding effect, okay? And these virtual photons basically can create electron-positron pairs as they're floating around, okay? All right. And what this does is that effectively, right, when you're far away from this far away from this electron, these virtual particles, right, actually partly shields the actual charge of the electron. This is known as the bare electron, right, where you actually have the real charge of an electron. What we see from far away is actually partly shielded by this. So when you have an electron passing by, right, these other electrons and positrons are partly shielding it. Okay. So the coupling constants for electricity and magnetism actually goes to infinity, but we're talking about Q squared of I think 10 to the 270. Okay, this is much higher than the Planck mass, right? So I think mass Planck is about 10 to the 19 GeV. So even if you square that, you get a 38. You don't go anywhere close to 270. Okay. So how is this different for the strong force? The strong force is different. It's completely opposite. Okay. because if you switch those electrons out for, let's say, charms, right, GC bars, right, normally you would just have a gluon exchange between them with a scattering. Let's just make it regular charms, just 2 charms, okay? But, right, now, right, if you have a charm by itself, right, and you're making gluon all around itself, these can also turn into maybe up bar quarks, right, which has no charge, right? The problem is that these gluons are charged, right? Now you have just additional charge, right, around when you are probing from far away, okay? So this is the reason why the strong coupling constant actually blows up to infinity as you go to low momentum exchange. Okay, so this is data from, I don't remember which experiment he took it from, but I think it's adapted from this review article from Bethke. Okay, where the strong coupling constant actually goes to infinity and actually decreases very quickly as you increase the momentum exchange between them. Okay, and this comes to kind of an interesting point. This is known as the running of the coupling constant, and it's actually the motivation for me to spend 4 years of my life searching for this thing called supersymmetry when I was working at the LHC. Okay, why did I spend 4 years? Because of this. Okay, so this is known as the unification of the coupling constant, and it's actually in this review article from Dimitri. I don't remember his last name, but this article is here. So if you were to plot the inverse, the reciprocal of the coupling constant as a function of q, right? Q, lowercase q, uppercase q. Let's just think about it as the absolute value of it. Okay. Since electricity magnetism increases, right, at high q square, right? Since we're plotting the reciprocal, it's going to go down as a function of q. Okay? We're doing the opposite. We're doing the reciprocal. Since the strong force, which is the one in blue, right, is going to decrease as a function of q, and then when we're plotting a reciprocal, it's going to go up as a function of q. Okay, the weak force, okay, alpha 2, is actually somewhere between the two. Okay, hopefully that makes sense. All right. So in the standard model, this thing SM called the standard model, when you project these coupling constants out, they don't actually meet in one place. Okay. If all 3 of these forces are the manifestation of the same physics, the same Lie algebra, the commutation relation we talked about before, right? At higher and higher energy, right, where the masses of them doesn't matter anymore, where you're at such a high energy, the chirality and helicity becomes the same thing, right? And all these strong, the charges, the strong charges versus the electric charges, they all become the same thing. You would think that, oh, they should, kind of do the same thing at these very, very high energy. You just have a superheated plasma, okay? In fact, I think this is the, when you go to somewhere, what's the units for this? To somewhere 10 to the 15 orders of magnitude higher than we do right now, okay? What happened is that the standard model coupling constant does not end in one point, okay? So the 3 coupling constant does not cross. Does not cross. It's at the same point. And what I got attracted to is this thing called the minimal supersymmetric model. Minimal. So I don't know why there's a double M there. So MSSM means minimal symmetric model for modification of the supersymmetry. Okay. And what this does is that you add a few more supersymmetric particles into your, the 17 we have already. If you were to do that, what happens is that it modifies how these coupling constants behave as a function of Q. And then if you tweak the mass correctly, okay, with certain masses, right, they all end up in the same place. Okay. And to me, that was kind of magical. It's like, wait, because in the beginning of the universe, when everything is super hot and super high density, all these different forces should not care about which, am I carrying an electric charge? Am I carrying a strong charge? Am I carrying a weak charge? Right? Does not care about that. And therefore, it makes sense for them to be the same. So this is the reason why I wanted to make sure to cover this in case you do see this argument for supersymmetry and the grand unification theory, where you're trying to pull all these different electromagnetic, the strong, the weak, and gravity eventually into the same theoretical framework. Okay. All right. So the last thing I want to cover is a little bit about hadronic collision. So Thomson snuck this in at the end of chapter 10. So it will be. I'm not going to do a lot of the details about it, but I wanted to just kind of show you the gist of what he's covering here. So when you have, so I think in this case is a proton anti-proton collider, which is actually the tevatron, not the LHC. LHC just collides protons and the proton into each other. What's actually being exchanged between them, right, are the partons of quarks or gluons. Okay, these partons, right, can exchange annihilate, for example. So you have quark annihilation here. Okay, and in this case, right, it annihilates through the photon, but this could also be a gluon. It can also be a Z boson. This is actually known as a Zhao-Yan process, named after these two people called Zhao-Yan. Okay, but you may see this word Zhao-Yan, but the idea is that you annihilate two particle and antiparticles together, and you make two new ones. Okay. So and this new particle decays into a maybe two leptons, such as a mu plus and a mu minus. If you were to go and plot, right, you have P3, P4. So if you add P3 plus P4 together, you square it, what you get is the invariant mass of the system. And that invariant mass is going to tell you whatever mass square of whatever was made during this Zhao-Yan process. Okay. And this is a measurement, right, from the CDF, from the tevatron, which stopped running, I think, in the early 2000s after the LHC turned on, where what they did is they just plotted this, they took P3, P4 of these muons, added them together, calculated the invariant mass, added them together, squared it, right? And what they saw is, these black data points, and you notice that there's a peak right here at about 91. Okay, GeV. Okay, and this is exactly the mass of a Z. Okay, and this is how a lot of particle physics search goes, where you find a particular process, and then you try to figure out what its invariant mass is. Because what happens a lot of times is that when you collide things together, you actually have you're in a different Lorentz frame from the mass frame, from the lab frame, right? So this collision can be happening in this direction or this direction, right? But if you calculate any Lorentz invariance variables with this, right, it doesn't matter if it's going to the left or to the right. You always have the same value. And, the mass is actually one of the best thing to search for. In fact, right, if you fast forward about 20 years, right, there was another particle found at 125 GeV, right, and that's the Higgs boson. Okay. Another useful variable, so especially those working on any LHC experiment, is this thing called the called rapidity. Okay. So in a lot of experiments, instead of using the angle theta, so maybe down here, theta is equal to like 5 degrees, 10 degrees, this will be 30 degrees, and this will be 45 degrees, right? What happened is that the angle theta doesn't actually corresponds to a Lorentz invariant quantity, okay? A Lorentz invariant quantity is actually known as rapidity, okay? It's basically defined with this y here is 1/2 the natural log of the energy plus the pz of whatever particle is coming out divided by the energy minus pz of the particle that's coming out, okay? This is Lorentz invariant, okay? But it's hard to use because a lot of times you don't know the mass of the particle, so therefore you can't actually separate, oh, is this energy or momentum, okay? So in the high energy limit, this function actually approaches a much simpler relation to relate it to theta, okay, known as pseudo rapidity. And this is using the letter eta, and eta is actually defined as negative natural log of the tangent of theta over 2, okay? So if you want to calculate, eta for theta equals to 5 degrees, right, you just plug it into this formula, okay? 2.5 degrees, and then you have that value. This is going to be approximately what rapidity is in the high energy limits, which is where we are most of the time anyway if you're smashing things together at 14 TeV. All right, so that's all I have for this section, and hopefully they will be useful, and then we'll work on the homework for these in class. Thanks.